Hi, and thanks for tuning in to the CBA Podcast, a place where we chat about our own recent achievements in the area of electronics, software and mechanical engineering, and more likely than not, give excuses for not having done anything at all. Hello and welcome back. It's been 3 weeks since the last episode. You would think I have a lot of stuff to talk about. I have not. I only have 5 items on my little checklist I have here. So let's do that. Also, this is the second time I'm recording. First time the audio recording stopped for some reason. It's not a big deal. First recording was a piece of shit anyway. Doesn't mean this is gonna be better, but let's try again then. First little thing that was a bit weird. When opening a LED, 230 volt LED bulb spot thing, I saw 5 or 6 SMD LEDs mounted on a aluminium PCB. That's not weird. However, when measuring the forward voltage of these LEDs, it was not 2 or 3 volts, but 45 volts, and I never saw that before. I think I saw a video done by biglive.com on YouTube, at least I think it was him, where he showed a big LED die, or at least what looked like a big SMD LED, with a forward voltage of 100 or maybe even 200 volts. These things were quite small, I think 5 by 5 millimeters or something like that, so I was quite surprised. So I think what's going on is the die has a number of LEDs in series, and 5 or 6 of these LEDs were placed in series. So the power supply of the LED spot was nothing more than a bridge rectifier and a smoothing capacitor, and an EMI capacitor I think, and not much else. So that was quite simple, but it works. Quite a while ago I made a video about doing electronic prototypes, methods of making electronic prototypes, and even the last or the episode before that I talked about making electronic prototypes using a copper-clad PCB and hand milling isolation slots in that using a Dremel tool or something like that. Now, if you want to make a big setup or a bigger setup for a demo or a test or something like that, and it has to be a little bit robust, so you have to be able to put it in your car and it should not break when you put something on top of it or if you drop it. What I normally do here is use DIN rails and DIN rail components. So what I do is I take a wooden board, like 12mm MDF for example, and cut it to size or have it cut to size. Mount a DIN rail onto that. I use rivets, that's easy, or screws or whatever. And then at the side of the DIN rails I put 2 parallel cable ducts, or I make a U shape using cable ducts. Then use DIN rail components to do the big stuff, for example relays and fuses and indicator lights and switches. And mount all the specific stuff that doesn't fit on the DIN rail on the board using screws or whatever. So in this case it had a motor of a fan, and I would mount that with 2 metal brackets onto the board, and leads from the motor would go into the cable duct and then nicely tucked away. And the only thing you would see was cables and a nice neat cable duct, DIN rail components and my own stuff on there. So at one end you have a mains lead going into the mains, and on the other end you have your specific stuff, your electromechanical stuff. And that works quite well, I think. It looks quite nice, it's quite safe, or at least you can hide all the dangerous stuff in the cable duct. Isolated quite well. DIN rail components are, at least I think, high quality. They should be because they're expensive enough. I paid a lot of stuff for this. However, you can recycle it every project. So if your project's done, you can take all the DIN rail stuff off the DIN rail, toss away the board and the DIN rail and the cable duct, it doesn't matter. I have a box here with DIN rail components like power supplies and switches and relays, and I just take what I need from that box. And a lot of terminal blocks and a lot of fasteners and so on. And DIN rail itself almost doesn't cost anything, so that is quite a method to make a cheap yet sturdy electronic setup with bigger electromechanical things on it, like a motor or a light or something like that. I think a couple of episodes ago I talked about taking apart a small drip coffee machine because I didn't know how it worked, and I took it apart, so a hollow heating element, and I assumed that a heating element would evaporate all the water needed for 1 cup of coffee, and then the water would condense somewhere else and drip through the water powder into your cup. However, I talked with a friend of mine about this, and it doesn't make a whole lot of sense from an energy waste point of view, because the energy needed to evaporate 1 unit of water at 100 degrees from liquid to vapor phase is about 10 times as much as heating it up in the first place from 25 degrees to 100 degrees. So it's a ridiculous waste of energy to evaporate water just to move it a few centimeters and that it condenses into a coffee powder reservoir. So that doesn't make a whole lot of sense. After talking about this, we thought of two solutions. One was that the hollow heating element had a one-way valve at the entrance, so water could only go in and not go out. And during heating, the water would expand, and the extra volume would be pushed out of the exit end of the hollow heating element into the coffee powder reservoir into your cup. Now, I didn't do a whole lot of research, but what I read was that the volumetric thermal expansion coefficient of water, that's basically how much water expands, or how much a volume of water expands in percent, let's say that, when it's heated up per degree Celsius is such that if you heat it up from 25 degrees to 100 degrees Celsius, it would expand by about 1.6%. That's not a whole lot. So I think the water that's pushed out of the heating element is, that's probably not it. So we talked about this a little bit more, and what seems probable is that the heating element indeed has a one-way valve. At one end it could be because of gravity of the water reservoir or because there's an actual one-way valve there. So the hollow heating element heats up the water. Now the water touching the heating element at the inside of the heating element is at the walls of the heating element is starts to boil at some point, forms bubbles, water vapor. At the end or at the exit side of the heating element there is a narrow tube. Then the bubbles that are formed go up into the narrow tube, and it's not that all the water needed for 1 cup of water evaporates, but the bubbles that start to boil off take hot water, which is not yet boiling, up in the thin hollow tube. So the small amount of water that is boiling, that is evaporating, acts like a transport medium for hot water that is not yet boiling. And the water that's spilled out from the hollow tube is deposited in the coffee powder filter thing and then drips down into your cup. So you need to evaporate only a little bit of water to get a whole cup of coffee. So the bubbles lift up the hot water in the hollow tube. So seems like a nice mechanism. So let's assume it works like that. And if I'm talking crap now, then please send feedback and we'll discuss it. So talking about coffee and talking about getting electrical shocks, I think the last episode we talked about getting electrical shocks from a charged high voltage capacitor. This time I got a shock again from a coffee grinder. And it was quite an old device from 1960 or thereabouts, if I can believe the internet. And it was not mine, it was my mother's. And I completely broke it and tossed it away already, so I'll have to make an excuse for that. Anyway, what happened was, the device is a small cylindrical thing with a metal enclosure. It has a motor, you put coffee beans in it, you turn it on and it grinds the coffee beans. It has a two-way mains plug. We use 230 volts AC mains here, by the way. So it doesn't have a protective earth at the plug end. So I was assuming the metal enclosure is floating, because it should not be connected to anything basically. Normally when I use a device I put my hand on the metal enclosure to keep the coffee beans or whatever I grind in it from flying all over the place, and that's fine, I don't notice anything. But this time I was leaning with my other hand against the protective earth pin of the electrical outlet. Don't ask why, I have no idea what I was doing, but I felt a shock then, so I was a little bit surprised. Let the thing go and decided to figure out what was going on. I first checked if the metal enclosure was directly connected to one of the pins on the lead. No, that was not the case, so it was not that bad. Then measure the voltage between the device's enclosure, and the protective earth of the house when the device was powered on, and it was about 180 volts AC, so it was a bit much. Then simulated myself by using a 10k resistor. I connected the resistor in between the device's metal enclosure and the protective earth of the house using crocodile clips and so on, and then measure the voltage over the resistor while the device was powered on. The voltage was about 47 volts, so it would drop 47 volts over that resistor, and the rest it would drop over the internal impedance of the device, let's say that. So opened up the device to see what was going on, and indeed there was a capacitor parallel to the motor, mounted in a metal brackety thing with one lead. Well, it was mounted parallel to the motor, so one lead was basically at the mains inlet pin 1 and the other lead was at the mains inlet pin 2. So the motor was I think it was a universal motor. It's called a universal motor. It can be used for AC and DC, provided the frequency is not too much. And indeed I tested it. It runs off DC fine. It uses brushes and it has windings on the stator, I don't know how to call it, and the rotor. So the brushes I think generate a lot of spark, so to prevent the spark from affecting your household, there's probably EMI capacitor across the motor, and I thought that was it. That was the function of the capacitor, and it probably is. But still, what did it have to do with the enclosure? Because enclosure still should be floating. So capacitor looked like a normal capacitor with 2 leads, and the capacitance was about 300 nanofarads from one lead to the other. However, from lead 1 to the metal enclosure of the capacitor was about 155 nanofarads, and from the other lead to the enclosure as well, 155. So it was actually 2 capacitors in one. So you had capacitive coupling from either mains inlet pin to the enclosure. Well, it's weird. There's no function for that. There's no reason for that. And also, if the capacitor fails, let's say it fails short, then you have a short from, if you're lucky, the neutral to the enclosure, and if you're not lucky, from the line to the enclosure, because we have symmetrical wall plugs here, the symmetrical wall sockets here. You can plug it either way. So I don't know what is the line and what is neutral when I plug a device in. You shouldn't have to know. So anyway, that was a bit weird. I don't know how the regulations were back in 1960, but so that was the reason I got shocked. So thought about replacing the capacitor with something else, or adding a protective earth lead to the device, but screw it, just toss it in a bin, and next project. So that was that. And last and least, I finally got an angle grinder. Piotr has brainwashed me enough to get one. I think it was a €50 device, or €49.95, not quite 50. It has a speed control. It's nice and yellow, and to be honest, I didn't even use it yet. I turned it on, verified it worked, and turned it off, and I was sitting somewhere. So I have a lot of stuff that I have to cut up inside the house, a lot of big stuff, metal stuff. So that will be put to good use, but I didn't quite, I wasn't up for it yet. So we'll see. So that was all for now. For more information, links and previous episodes, visit podcast.cba.si. Stay tuned, thanks for listening, and goodbye.